Hey everyone, in this video I'm going to continue talking about 5.4 non-Mendelian genetics and the clues to recognize these causes for rejecting null hypotheses in chi-squares. So in this video we are going to be focusing on linked genes, and linked genes is one of the ones that's commonly asked on the AP exam because of the additional step that we can take when it comes to linked genes. So linked genes are genes that are physically close together and that are usually inherited together as a pair. So they have to be on the same chromosome. And these were discovered by Thomas Morgan studying fruit flies. Now, linked genes contradicts independent assortment. So independent assortment states that the genes are going to sort independently, and this is mainly during metaphase 1, so homologous chromosomes on either side of the metaphase plate. But linked genes don't do that. Because they're physically close together and on the same chromosome, they're going to be inherited together. So the example that I typically give students is red hair and freckles. So if you know somebody with naturally red hair, they probably have freckles. And the reason why is because let's say that these are homologous pairs and they're going to go through crossing over. And what you see is with the red mark here is the gene for red hair. Now freckles is just next to that area. So even if crossing over were to take place and we were to cut this section of the chromosome off and pass it over to this one, so even if crossing over took place, because they're so physically close, the chances are that these two characteristics are going to get inherited together, even if crossing over take place. So linked genes are physically close together on the same chromosome, and they're usually inherited together. And that's what a linked gene is. So how do we know if a linked gene, or how do we know if we reject a null hypothesis because of a linked gene? So one of the ways you can tell if you have linked genes with the offspring, they're going to have a particular combination more often than the others. So I'm going to use a simple example. I'm going to use a very simplified example is what I should say. Let's say you did a dihybrid cross, and these would need to be dihybrid crosses. You did a dihybrid cross and you found, or you were expecting, fur color and curly tails in rodents. So you did your dihybrid cross, and what you determined was that the offspring should have been 50% red fur with a curly tail, 50% white fur with the short tail. And when you actually cross the organisms, what you find looks more like this. So as you can see, this is definitely not 50%, 50% the way that we were expecting. And so the question would be, why? Why did this come out so different? Well, in this case, what could be happening is that this could be an example of a linked gene. So in other words, that red fur, the code for red fur, is close to the code for straight tails. And so because they're physically close together, they get inherited as a pair more often than they should. So when you look at your expected numbers and you look at your observed numbers, you can see that the numbers do not match up. And so this may be due to linked genes. Now, the other thing about linked genes is that we can follow up with further evidence using what is called recombination frequencies. And we do that to map out the chromosomes. So what we would expect to see when we do these recombination frequencies is if we're suspecting that it's linked genes, then we should see that the distance between the code for red fur and the code for straight tail is very short. In other words, that the distance between these two, they are very, very close. They're not far at all. So let's look at how to do recombination frequencies. All right, so for recombination, understand that with those linked genes, the closer they are together on the chromosome, the fewer the number of times they're going to be recombinated. In other words, the fewer the number of times they're going to be separated. So you can think of recombination as how often do these two characteristics get separated from each other. And so the closer the gene, the closer the closer the genes are, the less times they're going to be separated because of that physical distance. And you can calculate the recombination frequency. So you can calculate how many times did these genes or did these characteristics switch up on in the offspring. And when you look at linked genes, the rate of recombination, or what we call the recombination frequency, will be very low. So that recombination frequency, or RF, will happen less than 50% of the time. So to calculate the recombination frequency, you just take the number of times that the offspring showed that recombination. In other words, the number of times that they separated those two traits divided by the total. And so if the number of times they separated comes out really low, so we're talking about our red fur and straight tail. If not a lot of offspring have that combination, then this numerator is very low compared to the denominator, and so your recombination frequency is going to be a very low value. Now, once you take that recombination frequency, they typically then convert this into what are called map units. And map units is kind of just what we call them. It's not an actual distance. When you can use those map units to figure out where on the chromosomes these genes or these traits are. So let's see how you use them. So let's say that you are comparing two characteristics and you have determined their recombination frequency. So characteristic A and B. This could be red hair, curly fur, or curly tail, whatever. Okay, and you are able to calculate the number of recombinants over the total, and you get that recombination frequency. That recombination frequency is going to be your map units. So let's say between A and B that the recombination frequency was 20. So what we would look at is that your map units, instead of saying percent, 20% recombination frequency, this would be 20 map units away from each other. And again, that's just kind of arbitrary. Now let's say we take another gene and we compare it to A as well. And when you take a look at the recombination frequency between A and C, you notice that the recombination frequency is 40 units. Finally, you calculate the recombination frequency between B and C, and you get that to be 10. And again, I'm just making these numbers up. So how do you generate a map from this? Well, number one, you want to start by identifying which of the two genes are the furthest apart. And you're going to know which are the furthest apart because they're going to have the highest map units. So from my data here, A and C are the furthest apart because they have the highest recombination frequency. So they are at 40. Then when you look at A and B, they're going to be closer together. And B and C are going to be closest together. So I'm just going to put my B. A to B is 20 map units apart, and B to C is 10 map units apart. So again, that recombination frequency is going to help you understand linked genes. The smaller that recombination frequency is, like here, the closer they are on the chromosome, and the more likely B and C are going to be linked. The bigger the recombination frequency, the farther apart they are on the chromosome, and the less likely they are going to be linked. I hope this video was helpful. Thanks for watching. Bye.